I'll go ahead and start recording now. So, just as a reminder for anybody who's joined the class, as a reminder for people who were here last week, but also importantly for the people who have just joined this class, all the lecture recordings of the previous lectures can be found by going to our Canvas page, then hitting this lecture recording button, or if you forget, hitting this link to the same lecture recordings over here. Both will bring you to this page where we get to this embedded playlist. For some reason it's uploading in reverse order. We'll see if I can fix that today. But basically here's lecture 1, here's lecture 2. It's an embedded playlist. So you want to watch those lectures if you missed them. You missed either lecture, make sure you watch them. Okay? Because they do describe, first one goes over the way the class is going to run, and my expectations. The second one goes over the textbook and how it works, pretty much. Again, it's a free textbook. Sign up for it with the instructions I gave out here. Today's lecture is going to be review of the material that is in the textbook. Now, one thing I've neglected to mention about the textbook is, although it wasn't really relevant until this week, is that when I assign these readings to you, I know that reading is like the worst for some of you. It is terrible. It is awful. It is boring. It is hard to concentrate on, even if it's short segments. So what I've done, and I did this during COVID, is that for every relevant section, I made a video that goes over basically the same material as in the textbook. Now, watching the video doesn't automatically check it off in the textbook, but you can. But basically, the idea here is you can either read the assigned portions in your textbook and go through it. You can watch the videos and just kind of flick through the textbook to just kind of get it checked off, right? Watch the videos instead of doing the textbook, or use the fact that I've given you both a textbook and videos that go over the same material in a different manner to your advantage if there's something you're having trouble with. And now you've got basically two resources there. So they're very good. Good. So yeah, I mentioned not every section has a video. As I bring up things in the video that make sense, like orders of operations. So, but you'll see there that the points like 2.7, 2.8, 2.10, those all reference the relevant section in your textbook. Okay. So this will let you know. Now, I also am not atrocious. I actually, before I made videos, I did a lot of research into how these things work. Like, for instance, this video is a 2-minute video. A lot of these videos are short. In general, the length from pedagogical standpoint, in other words, from looking at how we're supposed to teach things, the maximum length of a video should be 1 minute per grade level. So think about 13 minutes per maximum for a video in this class. And for most videos, they're much shorter than that. But I do try to break up the videos so that you can watch a video and either take a break or watch a bunch of videos and take a break. If you need to reward yourself for a job well done in some way, like do a death match after playing on a video game after a few videos, then you can do that. I just try to it's just when it's broken down, it's easier to do, So this will also tell you essentially what we are doing this week. So you'll attend Thursday and Tuesday lecture. Tuesday we'll have a Q&A review session and a short exercise. I might have time for that short exercise today. I'll just have to book it. But I've switched over to doing a game today, to doing a game which we will play later, because today we are talking about math for the most part and operations in Python. So if we boot up idle, okay, let's go ahead and I'll boot up idle on my end now, and then I'll describe it in more detail what exactly idle is. But the first thing I want to do is make it so that the people in the back can actually see. Let's go ahead and change that from Courier New to, come on, do we have anything better? Sorry, I'm a bit of a font snob. Cascadia Code, that's better. Okay. And I assume this is more than big enough for the people in the back, right? Right? Okay. When you boot, so first off, when you installed Python on your computer, you probably it came along with a program called idle. Now Python is not named after the snake per se. It's actually named after Monty Python, the comedy sketch, right? And yeah, comedy group. And Idle is named after Eric Idle. So that's so we get a lot of stuff in Python, in the Python programming language, from Monty Python. So it is their stuff is pretty funny. Check it out sometime. But that's why it's called Idle. And when we boot up, now when you did your first program, I said, hey, press Control N or go to File and New File to start building a new program. And I said to think of this as your output window, the one that says Python and has a blinking cursor over here, right? You can use this also to do some very quick programming, but not like write a program that you can save. That just doesn't work well. This is good for testing stuff and displaying stuff. This is also the kind of stuff you would get if you boot up your terminal and you typed in Python. You'll get this same kind of interface. Give me 1 second. You get the same interface over here, right? We could run code like print hello, and we basically are able to run code one line at a time. So first thing I want to do is basically kind of show you the power of Python's as a very powerful calculator. Now, as you know, Python, first we're going to talk about numbers. We're going to work first with the most basic type of number, which we call integers. Now, you can add integers together. You can add very large integers together, and Python handles it no problem. Not a single problem with adding big numbers together, right? If you're coming from a prior programming language, you possibly had to learn, integers such as ints and longs had certain limits about what kind of, like around 2 billion for integers to basically say, hey, these are the maximum size numbers it can store. Python don't care. Python says if your integer needs to be super big, we're going to make room for it to be super big. Okay? So it's less for people who are learning to have to memorize. And yeah, negative numbers are perfectly fine too, right? So we can add, we can subtract. And if we can add and subtract, then it makes sense that we can multiply very large numbers together, right? And small numbers too, right? So we can use it like a calculator, is basically the point. Okay? Now, before I move on to division, I want to talk about just kind of clarify, because I used a mathematical term, and not everybody here has a math background. And that mathematical term was integer. Integer are basically our whole numbers. They can be positive, they can be negative, or they can be zero. But they are our whole numbers. They are numbers without decimal points, right? Make sense to everybody? Okay? We have a different word for those numbers with floating points. And we need these floating points because we can't do fractions on a computer, right? We don't really have a good way to represent that. Try typing that out. It suddenly becomes a nightmare. So we do decimals. We call these decimal points, or points with a floating point in them, floats. F-L-O-A-T. Float. Other programming languages call their things doubles. They call these things doubles. And the reason they do that is because that is double. Double is short for double precision floating point. Okay, but in And so other programming language will have float and doubles. Python just has float, and they are equivalent to other languages' doubles. And these work exactly the same. You've got 1.5 times 2.0, and that becomes 3.0, right? I multiplied a float against a float, and it gave me back a floating point number, 3.0, right? Even though it could have written 3, because it's a floating point, it's going to display as a floating point. Can I add these? 1.1 plus 1.2 gives me 2.3. I try to keep the math either completely incomprehensible or very easy to do in your head, right? There's no in between. Like here, I would not expect you to be able to do this math in your head. This is just me hammering on the keyboard to make a point about size, okay? Otherwise, I will keep math. Any math that has to be done with actual numbers in this class will be done at very simple kind of stuff like this. This is not the math class. This is not for me to test you on those kind of things. I have other math-related things to test you on, which I will talk about in a bit. Okay, 1.5 times, 1.5 minus 0.5 will give me 1.0. And so we can see we can add, multiply, and subtract these numbers as well. We can also do, let's see. Oh, and then I suppose there is one more question, because I did this over here, 1.5 times 2.0, but a lot of the times it's more natural for us to write 1.5 times 2, right? Where we don't have 2.0. Is this kosher? Is this okay? Right? Yes, it is. So you can mix and match integers and floats. You can mix your integers together with floats. The key thing here is that whenever we match integers with floats, we're just going to convert those integers to floats. So that, because if we did it the other way around, we might lose some data. Okay? Make sense to everybody? And what data might we lose? The stuff after the floating point number, right? Makes sense? So we can mix and match these things. So when I multiply a float and an integer, I get a floating point number. So we've got floating point numbers. So number-wise, we've just got two things. We've got our floating point numbers and our integers. Now, we went over 3 operations: add, subtract, multiply. These work exactly as you expect. And they use the operators you expect. Divide, obviously, since I haven't mentioned divide is a bit different. Dividing with floating points works exactly like you'd expect. 10 divided by 10 point, let's go with 10.0 divided by 3.0. And that gives us 3.333335. Now this 5 is a little bit weird at the end. And the reasons to explain why we are getting a weird 5 here as opposed to 3 or a 4 or 2 is a bit complex, but long and short of it is that we are doing our numbers in decimal. I'm putting numbers into decimal. This computer, though, doesn't think in decimal. It thinks in binary. It thinks in ones and zeros, right? So it's got to convert binary here, right, is base 2, right? This is base 10 over here, meaning that every digit is a power of 10, versus base 2, where every digit is a power of 2. It's actually kind of interesting, but not relevant right now. I don't want to get too sidetracked. So we convert this into a series of bits, short for binary digits, and the computer does the math internally in binary, but it can't feed us binary back because of course, we don't understand binary, right? I've done about 10 minutes of coding in binary as part of a course, and the entire point of that was that 10 minutes were extremely painful, and that's why we don't do it. So when we convert it back, there can be some error there. Furthermore, we are representing this infinite repeating fraction, infinite repeating decimal of this series that can't be represented in a decimal system. We're converting that to binary, which also can't represent it, And so then we convert it back, and that just adds to that confusion. So that's why you can get some weird quirks there, okay? But long and short of it, again, we're talking about, this is part of the reason why significant figures are kind of important in chemistry, even when you're doing computer work, right? Because you just want to make sure, because at some point, only these numbers are really important. Okay. But the long and short of it is that I divided a float by a float, and I got float. I divide an integer by a float, and I get a float. And if I divide an integer by an integer, I also get a float. Now, for those of you coming from another programming language, this is anathema, this is unholy, this is an abomination unto the Lord. This is the, but for those of you not coming from another programming language, for those of you who this is your first programming language, this makes total sense, right? Of course, if I'm dividing and it needs to be chopped up in portions, I'm going to get a floating point number back. This is what I'd get if I plugged into a calculator, right? So, key to remember here is that when you use the division operation like this, when you use a single divide operation like this, you're going to get a floating point number, no matter what numbers you're using. Make sense? Now, as we'll see on Thursday, okay, sometimes it's extremely important for us, though, to just care about the quotient. We're about to do a lot of fourth grade math today. What do I mean by that? We're going to go back to long division, okay? What do I mean by that? Give me a second to boot up my whiteboard, which I don't have installed, so we are just going to go to Paint. I'm going to install it one of these days. Paint. Here we go. Brushes. How's my brushes? There we go. That's good. So what I mean is long division, right? If I'm doing 10 divided by 3, right? You've done this before, where basically 3 goes into 10 3 times, right? For a quotient of 3. And then there's this whole bit about subtracting there, and we can't go down any further, so we write 3R1 for 3 remainder 1. Everybody remember this? This giving you PTSD, right? So anyway, so we get 3 remainder 1. And we have these two important parts over here, which I will go ahead and circle in different colors. We've got our 3, which is the quotient, and our 1, which is the remainder. And sometimes it is very useful to get the quotient, and also surprisingly, it's sometimes useful to get the remainder. Okay? If I just care about the quotient, right? If I just care about the integer portion of integer division, I can get that. And to do that, we use 2 divide symbols. Okay? Divide, divide. 10 divide 3 gives us 3 because we can subtract 3 from 10 3 times. 10 divide 5 gives us 2 because 2 times 5 is 10, right? Make sense? Okay? And this shows up on my exams a lot, or something like this shows up on my exams a lot. 10 divided by an enormous number gives us 0 because we can't divide that, because there's no way that I can put this number and divide as the divisor to this number and get anything out meaningful, right? Right. So often on an exam, in one of these kind of questions, I will ask something along the lines of big scary number divided by big scary number, and it ends up being 1 or 0. So, okay. So that's kind of useful there. We'll see why it's useful specifically on Thursday when we go over an exercise that will be useful for the fourth part of Lab 2. Fourth part of Lab 2, for those of you who haven't taken a look, is writing a converter that takes in a number of seconds and gives you the number of hours, minutes, and seconds that is equal to. Okay, so for instance, you put in 5,000 seconds and you get, I think it's you get 1 hour, 22 minutes, and 23 seconds. I know this because that's what I always tested on for thousands of students, so not because I could do the calculation in my head. But anyway, we'll find that in order to do that, we're going to make judicious use of this operation, so we can get, this is how many minutes it is, but also the other operation, the modulo operation. which is a very fun operation here. Okay, so 10, going back to this example, right, where we did 10 divided by 3, if I do this operation, and this is an operation you only ever really see in this class and in higher level mathematics, even though it's not that hard. And we use the percent sign here. If you're coming from higher level mathematics, you're looking for this word, mod. But here we just simply use percent sign. 10% 3 gives us 1. 11, actually let's do 13 mod 5 gives us 3. Let's go with 1,255 mod 10 gives us 5. Mod, you can effectively think of, there's all these beautiful mathematics that go behind modular arithmetic and stuff like that. But you can think of modular arithmetic like it's the remainder operation, right? It is just like divide gives you this number over here, right? Divide gives you the quotient. What modulo is going to do, modulo over here gives you the remainder. Make sense? It gives you the remainder, which is extremely useful in a lot of unusual circumstances. It's fantastically powerful. We'll go back, and I think that's actually where I need to be for our game. Okay. So let's just talk about a bit more about modular arithmetic. A lot of times what we're going to do in this class to do modular arithmetic is to use it more as a tool than as a calculation. It's a weird way to think about mathematics, by the way, to think of these operations as tools to use on numbers. But let me give you an example. I've got this number 1, 2, 3, 4, and say I want to chop off the ones place, okay? To chop off the ones place, just to get to chop off the rightmost digit, because I can, okay? How do I do that? I can divide by 10. Right, I can do that. I can divide by 10 and not care about the remainder or the floating point. Just simply do that, and I get 1, 2, 3, right? Because dividing by 10, we get rid of the ones place. Similarly, 1, 2, 3, 4, if I mod by 1,000, that's the remainder after I divide by 1,000, which gives me everything but the thousands place. It chops off whoops. I accidentally highlighted and pressed enter, so that's what happened there. 1, 2, 3, 4 mod 1,000. So that gives me that chops off the leftmost digit. If I only want to get the rightmost digit, and you don't have to memorize these things. I'm just saying these as things that they will crop up and you'll see them be useful. You kind of discover them on your own or rediscover it on your own. Whoops. 1, 2, 3, 4. Modding by 10 gives you the ones place, right? The remainder of anything divided by 10 is the ones place. Right? The remainder after you divide by 10, and when you divide anything by 10, is the ones place. So this gives me 4. Or another way to think of it, gives you the rightmost digit. And probably the one you'll use the most is to check if a number is even. If I take a number and mod it by 2, okay, any number and I mod it by 2, doesn't matter how big it is, all I have to do is look at that last digit. If I mod by 2 and I get back a 0, it was evenly divisible by 2, so it's even, right? There's no remainder. So, or the remainder 0 is another way to put it. So it's an even number because it was cleanly divisible by 2. If, on the other hand, it is a number that is not, if I get back a 1 when I mod by 2, it's odd. It wasn't evenly divisible by 0, right? So it's kind of useful to see when in a formula when we're doing this. I haven't talked about variables yet, but you kind of remember them from mathematics, and I will talk about them in a bit. I figured I'd talk about numbers and operations first, Okay? And I kind of got to the modular arithmetic. So we're going to just take a break with our game here. Now, for those of you who don't know, I love games. Games are good. Games are a lot of fun. So, let's see if I can get this here. It was so much easier. I was able to do it. I was able to do a lot better in my previous classroom. Lecture hall. But at least for the recording. But environment. All right. More sources. Document camera. Now, there's a particular game I love when I teach algorithms called NIM. NIM is a very interesting game because it's extremely well studied. And the way NIM works is that you take a pile of objects, right? You take some pile of objects, it doesn't matter what they are, and you split them up into 3 piles, let's say, for candy. And the idea here behind NIM is you can play one of 2 ways. And the way we play, at least in this class, is that you don't want to be the person who takes the last piece. Now, the way you can play is on your turn, you get to choose one of these piles, okay? And you can take as many as you want from a single pile. So on my turn, I could take away this pile and grab everything, right? Or I could just simply take one from a single pile, right? I can only do an operation for a single pile. Now that involves actually doing some. Now I use this game when I use NIM itself when I teach binary. But I'm not teaching binary right now. I'm teaching modular arithmetic. So we play different games when I teach modular arithmetic. One with a bit of a higher stage, shall we say. When we do modular arithmetic, I do chocolate chili roulette for teaching modular arithmetic. This is a jalapeno. You do not have to play. And certainly don't play if eating a slice of raw jalapeno is not something you can handle. Can be a bit intense. Right? So that should be more than enough. Okay. Chocolate. And right, so the idea here is that we've got a bunch of pieces of chocolate, and we've got one piece of pepper, hot pepper here. So the way this game works is that on your turn, you can take 1, 2, or 3 pieces of candy. 1, 2, or 3 pieces on the board of either chocolate or the pepper. And obviously, you do not want to be the person who takes the pepper, right? So the way this will work is that my intention is that I'll play this game with any volunteer, and my goal is to continue playing with members of the class until I am forced to eat a pepper. I should point out that, at least for the first game, it won't be possible to beat me unless I majorly mess up. But from every other game going on, I will go second, in which case it will actually be possible to beat me. But as long as I can go first, and there is an appropriate amount of candy, which I counted out in beforehand, then, at least for this first game, anybody who's playing is going to be forced to eat that pepper. So, just FYI. So, any volunteers? All right, yes. Come on up. It's fun, and you get candy.
Yeah, I'm doing this for you.
Excellent. And I've got extra here and I've got extra Starburst over here in case you need them.
Yeah.
Okay, so on my first move, I'm going to take 2 pieces of candy. So it's your turn. You can take 1, 2, or 3 pieces. And take 3. You took 1, I'm taking 3. I'll take 2 as well. You took 2.
So the person who's eating the pepper is the one who takes the last thing, right?
Right.
Okay.
Yeah, you're. Yeah.
Just wanted to make sure it's not like.
No. But if you take, no. Basically, if I take the pepper, sorry, if there's nothing left for you to take, you have to take the pepper.
Oh, okay.
So, I'm going to take 2.
Yeah. Taking the pepper.
And then I take 3.
Do I have to chew it?
You have to just bite it. You don't have to like eat it or whatnot if you don't want to. Hot, yeah.
Yeah. Not bad.
Not bad. All right, everybody give a hand. All right. Now, this is one of those solved games. It is a completely solved game, meaning that we can figure out where we are. Meaning that whoever goes first can kind of control the game, assuming that the appropriate amount is given out. Okay, so different amount. This time we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And let's go with. So now we have 18 pieces of candy plus a piece of pepper. So this time, and for all other future games, I will go second. If nobody wins this time, I will then. So second time, you can try your hand, but I will reveal the strategy after this. Okay? Because I'm just using math here to make sure that I win. Yes, come down. Let's go ahead and make it easier to see for the camera. All right, what's your name? Hannah. Hannah?
Yeah.
All right, Hannah. So it is you. So you get to go first. There's a grand total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 pieces of candy. All right. All right. All right. Good job. Now, everybody give a round of applause. Now, I got questions for both of you now that you both played the game. When did you realize you lost? At what point? This is important, actually. There's a reason for it. At what was this? Do you remember the board state when you realized you lost? Because I was paying attention. I know when you realized it. The same state, it's the same time everybody realizes they lose, which is when the board state looks like this. Okay, when the board state looks like this, and it is your turn, what happens? We're kind of in a solid position. You eat. If you choose 1, I choose 3. If you choose 2, I choose 2. If you choose 3, I choose 1. I'm not going to obviously choose to have that piece, right? So, what's going on here? Well, the number I'm choosing plus the number of you choose adds up to 4, essentially. So if we extrapolate to now back a step and add another 4, if you choose 1, I'm going to choose 3 so that we get down to that state. And if we aren't here yet, right, and you choose 2, I'll just choose 3 and get us down again to this state. The entire point is for me to get a number of pieces left that is divisible by 4. That is my trick there, using modular arithmetic. Now, if we weren't playing with candy and just simply said, the person who takes, let's say, the orange starburst loses, okay? It's a bit harder to think about it this way. Then my goal here is actually to say that the number that the board state should be the number of pieces left modulo 1. Sorry, modulo 4 is equal to 1. In other words, the number of pieces that the remainder after dividing by 4 should always be 1 in this case. But with candy, it's a bit easier just simply with this case, it's always easier to ignore it and just say, oh, I want to play so that I'm taking the last piece of candy. And then the M&M, and ignore the pepper and begin with them. Just simply play to take the last piece of candy. And as long as I'm doing modulo, as long as I'm making sure that the number of pieces that are left after I take is divisible by 4, I'm good. So again, over here, right, I took, it was my turn, and so if it's your turn and you've got a number divisible by 4 left, you're in trouble, right? That's also why I was counting out specifically in the beginning on yours to make sure that I wasn't handing you a number that was divisible by 4, because that would have been basically just forcing the loss on you anyway, you know. So, all right. With that in mind, would anyone like to come down and play? All right. All right. So let's see. So how many? So let's go ahead. And you get to go first.
Can I count them?
Yes, of course, please. How many did I give you?
22.
22.
Unless I counted them. Which would be possible.
Well, let's go ahead and group them up. Right? Now you counted right, 22.
Okay.
So the issue is that it's on your turn and you've got a divisible, and you've got the number of pieces divisible by 4. Yep.
I just lose.
Yep.
here.
Yeah, you want to just lose here, you're fine. You can surrender.
Yeah.
So on your first move, you should have taken 2 pieces, not 3.
Yeah.
All right. Good job. Everybody, round of applause. All right. One more, because after that, I'm going to probably have too much. I'm trying to lose weight, and you aren't helping here. Actually, 32 of these is a serving, so I'm not doing too bad, I think. So let's go ahead. All right, this time I have poured out 23 pieces of chocolate and 1 pepper. All right, who would like to play? You can try again, sure. I think revenge is only fair. All right, so we've got 23.
Yeah. This is suddenly more enjoyable.
I know, right? Now you know why I started doing this. All right, so my turn.
Thank you.
Now the real name of this game. All right, so that was fun. Now the real name of this. So as I mentioned, I love games. A lot of games have like mathematical. Woo! There's the heat. Okay. A lot of games have like mathematical theory behind them. And if you happen to love games, one of the things you can do for a final project, if there's a particular game you love, you can write a mod for that game. That's a totally viable final project. Now this game is more formally known as the subtraction game. But honestly, it's sometimes it's accidentally called NIM, which is the game I was talking about earlier with piles and stuff that I used to teach binary arithmetic. What's interesting though is that there's like about, I'd say tons and tons and tons and tons of games that are all mathematically equivalent to NIM. They can be converted into NIM. This game, the subtraction game, can be converted into NIM. There's a game called the 100 game that can be turned into NIM. There's a game where you remove line segments from a drawing that can be converted into NIM. There are all sorts of interesting things, and I love it when you can when you have Hackenbush, where you remove line segments. It doesn't look like this game would be mathematically equivalent to a game where you're removing candy from a pile, but it is. It is. It's weird, but it is. And the reason it's done is that they figure out how to convert it, and then they can convert that into you figure out how you can simplify these things, and then how that simplification can be converted into a pile. So it's very interesting. But the number of games where you know math and can do that stuff is actually pretty useful. We'll be doing quite a bit of our last assignment for the semester will be a game that's related to math called Pig, and that's a kind of a game of, it's a dice rolling game. But it's interesting. So we can now, so we've learned about our mathematical operations. There's a couple more mathematical operations I would be that are important to mention, because the biggest one that I find students have issues with is exponentiation. Okay? Right? Like doing 5 squared. Because you'd expect to write it like this. Right? 5 squared. Now 5 squared is 5 times 5. 5 times 5, right? I chose that example because pretty much everybody knows 5 times 5 is 25, right? So when I ask for 5 squared, everybody knows that the answer I should get is 7, right? The issue, of course, is that I didn't ask for 5 squared, right? If I did, I would have gotten something else. Obviously, this caret operation, as it's called, the caret, is something completely different. And it is. It has to do with binary arithmetic. You don't have to worry about it. Nobody's going to test you on it. It's not something to worry about, right? You do not have to know what this does. Similarly, you don't have to know what this does or what this does. Whoops. Well, that does nothing, obviously. Or this does. They exist, but you don't have to worry about them. Just, you'll see them occasionally, and if you find them in a program you find interesting, come and ask me, and I'll be happy to answer what they are. Okay? All you have to know is that this is not what you wanted when you wanted to do exponentiation. Okay? This is actually the XOR or XOR operator, which is weird. Instead, what you want to do for exponentiation is, and the reason this isn't exponentiation is because that was reserved a long time ago by the XOR operation. This was done. This meant XOR for computer scientists a long time before this meant doing exponents when you were typing. So as a result, we do a different operation that actually makes a lot of sense for doing exponentiation. Since exponentiation is just repeated multiplication, we use 2 multiplication operators. So this is 5 squared. And this is 5 to the 5th power. And again, your computer is rather good at producing, exceeds the max digit for strings. Okay, so its issue with doing this math wasn't calculating it because it came back pretty darn quick. It was being able to print it back out to me. So it has no issues doing this number crunching. Number crunching is what computers are really good at. Okay? So now that we know these things, we should talk about order of operations very quickly. Fortunately, you already know it all. Pretty much all of it. Okay? Order of operations you've already learned in algebra, right? Please excuse my dear Aunt Sally. All the rules that are in mathematics apply here, right? You do parentheses first. Let's do 1 plus 1. We're going to keep it nice and simple. 1 plus 1 times 2 divided by, let's go with 4, right? It's going to do this first, then it's going to do the multiplication, then the division, right? And remember, the way it works is that multiplication and division are the same tier, right? Multiplication and division are the same tier, so it's whatever we do that's left to right, right? On the other hand, if we see this, right, 2, this is the same answer, but I'm just writing it differently. 2 squared times 4, that's also 1 because we do exponentiation first, right? Or maybe another way to put it is, right, we do exponentiation first. Right, please, for parentheses, excuse for exponents. My dear, right? Multiplication, division, and then Aunt Sally, AS, for addition, subtraction. Again, addition and subtraction, you do whatever you see first. It's not that addition takes place before subtraction. It's just whatever you see first in addition and subtraction, you do it first from right to left. Okay? So that just leaves one question. Where the hell does this end up in our order of operations? And the answer is, this is just division. It's just giving you a different answer, right? You have to do division to figure it out. So it's division. Modular arithmetic, you can now just simply plug in M for multiplication and modular arithmetic, right? It's the same. It's a division operation. It's the same thing. Make sense to everybody? So order of operations still matters. It's still basically the same stuff. And that's a grossly exaggerated lie, but it works for this class. So let me talk briefly about what I'm lying about. I just showed you a bunch of other operations here. They have orders of operations. They have precedence. This has precedence. It has a precedence, but you already know it. You do it. Sorry, whoops. Darn it. 4 plus 5 is less than 10 plus 1. You already know the order of operations for this. The less than sign occurs after all the math you do, because how can you compare them if they're not already done, right? You know that stuff. There's a whole order of operation chart you can look off of, but if you've been doing math, you already know the important bit, which is you do the math, and then everything else kind of follows. The only thing that really I ever find confusing is that you'll find out that there's operations for doing and or, and one of those comes before the other. Do you know which one comes first? I don't remember. I have to look it up every time, so don't worry about it. Just know that exists, right? So, at the very dead last in order of operations is one thing, and that's this: the equals operator. Our assignment statement. X is equal to 10. This is so these, what I've been writing so far, are expressions, right? They're kind of equations. They are expressions. They do something and they calculate something and then they produce what we sometimes call a literal, which is just like a literal number. It's not a variable or anything. Literal is just not a variable. Variables are things like this. You've seen them in mathematics. This sets the value of x equal to 10, right? And as I briefly mentioned on last Thursday, this equals operator, we call it the assignment operator. Because what we're doing is we're taking the thing on the right side, and we're storing it in a box on the left that is labeled x, okay? In fact, your textbook is actually probably the best place to kind of look at this kind of stuff, because if I'll just log into it for a second. All right, log in here. I'm going to go ahead and once I go to the textbook, there's this nice edit button, and this is accessible in any code block that you have, where you get this scratch pad. Okay, I'm just going to type here. Don't worry about not being zoomed in. I'm going to fix that in a second. X is equal to 10, save and run. Right, and then there is this button here called Show in Code Lens. Visualize that Python to edit code and get AI help. I don't need the edit help. I can just simply show here. But anyway, it displays this. It embeds this page in there. Okay, and so we can do x is equal to 10. Y is equal to 11, and Z is equal to X. Visualize execution. So over here on the left we get our code, and on the right we're going to get a visual representation of what we're seeing, line by line. Red is the next line that's going to execute. The green is the line that just executed. So I hit next. It just executed this line, x is equal to 10. So we have a variable called called x, and it stores 10 in it. The next line, y is equal to 11. We take what's stored on the right, and store it on the left. Y is equal to 11. Z is equal to x. We take what is on the right and store it on the left. But we don't know what's stored in here. It's x. It's a variable. So what do? We've got a box called x. We look what's inside it. It's 10. We take that value and store it in z. Z is equal to 10. So now the reason I refer to this is we've got this value z. Let's go ahead and say x is equal to 5 now, okay? Visualize execution. So let's go ahead. I added one line. Boop. So now we've got the same place we were. Z is equal to x. X is equal to 5. So this is kind of important here. We set x equal to 5. This takes 5 and stores it in the variable x, which means x changes, but z does not. Okay? This is a copy operation that copies the value on the right and stores it on the left. It is not a hard linking. It does not create a strong symbolic link between the two things. It does not say that x and z are always going to be the same thing. It just took what was in x and copied it. That can be unintuitive for some students when they're just starting out, but the reason we do it like this is because it's just bloody simpler. Because otherwise you'd have to remember all the times you set variables equal to each other and when they were tied together. And that's just too much to remember. It's easier to remember, okay, they're just boxes and I store these things, these values in their boxes. Okay. Now, as a result, that does allow us to do some weird shenanigans. But before I go into shenanigans, let's just talk about rules for variables. Variables are very powerful here, but you do not need to feel limited into just simply calling them single letters like you'd have to do in physics and in mathematics. In fact, the more powerful the editor you use, the longer you should probably make your variable, because the more powerful those autocomplete features are. Right now, I will use idle, but later on in the semester, I will use something called Gini, which is it doesn't have it. Interesting. Okay. Oh, I'll have to reinstall it. Okay. I've got an editor called Gini, which I use instead of VS Code because it is a lot less powerful in terms of its autocomplete. It figures out what to autocomplete by basically just looking at all the things you've already typed and only autocompleting there. But once you have an autocomplete feature, once you type a variable once, it's very easy to type again. So there's nothing stopping me from going seconds is equal to like that. Okay? Seconds is equal to 5, something like that, right? And there's no issue with me making a variable that is a bit bigger. Okay. Now I've got some other stuff I want to, if I have to, we will do both exercises on Thursday because there's plenty of time for that. I just want to make sure I hammer these points home. Okay? So, the last thing I want to talk about with variables is that you really have to learn how to use them, again, kind of by doing them. That's why I want you to do these exercises in the book. I want you to do the labs. That's the best way to learn it, as opposed to, and of course what we're going to do on Thursday will help with that. Okay? But the important thing to understand here is that because we are taking the value, we are calculating we are basically computing the expression on the right, and storing it in the thing on the left. So thing on the right gets stored in the left. Because we're doing it like this, we can get rather interesting lines of code that would normally be nonsensical in mathematics. The kind of things that a troll writes down on a Facebook post to say, ha ha ha, and now I've disproven mathematics by saying 1 is equal to 0. In this case, though, it is perfectly okay for us to say something like this. Okay, let's go through it. So let's go ahead and just kind of go through it line by line. Remember, this is an assignment statement, not an equal sign. 5 is stored in X. Then we're going to compute the thing on the right and store it in the left. Right? That's 2 separate steps. So we're going to compute the thing on the right. X is what? It is 5. We know it's 5 because that's what this says. X is 5. 5 plus 1 is 6. Easy math. I said it would just be easy math in this class. So 5 plus 1 is 6. This becomes 6. So we store 6 in the variable on the left side of this equal sign. That variable just so happens to be x. It could have been anything. It just so happened to be x. So 6 overwrites 5. Make sense? And print x. This is useful if you're using a single variable to do a lot of counting and stuff like this. So we'll see this from time and time again. So that's enough about about numbers for a bit. Okay? So let's talk about something other than numbers, right? So we're going to be working with 3 main types for a while. The first type was integers. The second type was floats. And we've been talking about all sorts of operations we can do with them. The last type is strings. And we've already kind of worked with them in our beginning lab, which is Lab 1, the Hello World. Strings are text because humans need text, not just numbers. Okay? Now, a string, because we type a lot of stuff into a computer, like variables like seconds or variables like x, we need a way to know, or some numbers like 10, we need a way to know that we're talking about text rather than variables. Make sense? So the computer knows that we are talking about a string of text if we use quotation marks. They can be either single quote or they can be double quote. And when I just do this, and by the way, when I'm just simply typing the word without print, all it's doing here is just executing the expression here and automatically printing the result of that expression. It's one of the reasons I'm working in the repo right now, so I don't have to keep writing print. Also, this format makes it less likely for you to try to write it down. It's not important for you to write this part down or to type it down, because I'd just be erasing the code left and right anyway if it was a file. So strings are text. Now, if you're coming from another programming language, you're probably like, wait, no, this is a string and this is a char or a car. It's all strings. All strings. Python was like, there's no reason in current year to basically differentiate between some text that is 1 long and some text that is a lot long. Okay? So all text is there. We have various operations we can do on this because behind the scenes, these are all everything is represented in binary anyway, so these can all be represented as numbers. And it is UTF-8 compliant. What does that mean? Japan. Boo. Japan. Nihon. And also I could just simply do I could also, have this as a quote. So any arbitrary language of your choice pretty much works in this, as well as emojis, which is pretty interesting. And the reason this works is because these are all based in Unicode. All these symbols are on a list, and you can find out what order it is in the list by asking, hey, what is this in the big list of Unicode? And this symbol is number 26,000. And what's cool is, and I'm going to show this off way later in the semester. Maybe, and by way later, I mean maybe in a week or two. you can do the opposite. Ask, given an arbitrary number, what is that symbol? There's a lot of symbols there. Okay. Again, UTF-8 compliant. So strings are pretty cool. They're text. We basically use them for printing out stuff and for communicating with the user. So there's two important things we need to do when we're working with text. First, we need to know what operations to do in them. Okay. Which are these operations, right? Which is, do any of these make sense for working with text? And the other one, which I'll do first, is conversions. Because a lot of times when we use something called the input function to get stuff from the user, whenever we do an input from the user, asking them to enter something on the keyboard, that's going to always come back as a string. In fact, the vast majority of data that you ever read is going to be strings because it's going to be stored as text. So if I read some string in, like 55, right? How do I get this to be converted into an integer, right? So I can actually use it in math, right? Just like how in lab 2, I ask you to enter, if you've looked at it, I ask you to enter the height, the weight, and the age, right? How do I take this and turn it into data I can actually do math on? I need to turn it into an integer, and we have 3 functions for doing type conversions. Int takes something, and if possible, converts it into an integer, right? Int for integer. Make sense? Float takes that something and converts it into, guess what? A float. And then finally, str, which is short for string. You're never going to believe this, but you can take anything you want, and it's going to convert it into a string. So for each of those 3 data types we have a function here in action built in. That's why it gets the purple text, because it's built in. You get an action, a function that converts it into that type. Now, of course, if I basically not of course, but Python tries to operate on the principle of least surprise. So if I do something like this, where I try to convert apple into a number, it's going to yell at me saying, hey, invalid literal, you gave me invalid data for an integer in base 10. It doesn't work. I can't convert this into base 10, right? This just doesn't work. Okay, if it was a different base, like base 32 or something, maybe, or something else that I might understand, hexadecimal base 16, that might work, but not this. Now, let's talk about string operations, right? Let's go with let's go ahead and restart shell. This is just simply going to clear out all the data, so I don't have any x anymore, right? I don't have any defined variables anymore, okay? Going to actually boot up idle so it's clear from the top. And what we're going to do over here is I'm going to say w1, or actually I'm going to call it s1 for string 1. s1 is equal to apple, assuming it can spell apple right, and s2 is equal to banana. The hardest part about spelling banana is knowing when to stop spelling banana. So, okay, S1, so we've got 2 strings, S1 and S2. Again, Python is going to operate on principles of least surprise. So adding S1 and S2 together, these 2 strings together, this is not a surprising result. This kind of addition operation is formally called concatenation, which is just a big fancy word for saying we glued these strings together, right? And this can be tricky sometimes because the only time this ever becomes tricky is this classic kind of question, CS 101 question on the exam, which is you've got string plus string, which gives you string, right? 4 plus 3 is equal to 43. They're strings. They're not numbers, right? I'm not a big fan of this question because it's a trick question, and once you see it like once or twice, you're good for life on it. But just know if you take it somewhere else, they can be very fond of this kind of question. Okay. Anyways, when you add two strings together, you get a concatenation. What if I add a string and a number? It's going to give me an error. Doesn't matter if it's a float or an integer. If I add strings and numbers together, or a number and a string together, right? It says can only concatenate strings to string. What if I do it the other way around? 4 plus S1. Unsupported operands type, right? Operands are are the sides of an operator, right? The two things that go into an operator. Unsupported operand types, int and string. Okay, makes sense. S1 and minus S2. Does that make sense at all? Not really, right? It doesn't make sense to subtract, to do apple minus banana, unless it's one of those weird Facebook posts that say only 5% of people are smart enough to get this right, you know? You know the kind of nonsense I'm talking about. Okay. And similarly for multiplication and division, although we got something very interesting, we got a very interesting error instead of what we got last time. It was an unsupported operand. So S1, but we're going to move on for a second. So we said unsupported operand for minus, unsupported operand for divide. But for multiplication, we got can't multiply sequence by type non-int of type string. You can't multiply a string by a non-int, which implies you can multiply a string by an int. And this is something that's built into Python that I don't think is built into other languages, or a lot of other languages. And it's utterly beautiful. It's great. So I'm going to do S2, which is banana, remember. Okay? And I'm going to do S2 plus NA. And I'm going to do this first. NA times 10. And we get banana. Okay? So, let's go ahead and actually see this in a bit of an easier result. If I do na, the string, times 3, I get na. Right? If I did if I do S1, which is apple, times 2, I'm going to get apple. Make sense? This is called replication, and it's very useful because there's some times where you just want to copy a string, right? And that's extremely useful. Like, there's just no way to undersell it. This is an extremely useful operation when you find you want to use it, because otherwise in other languages I have to do like a loop to do this kind of stuff. So those are the things that we operate with our data. Now, there was an email that was sent out that was erroneous, for one of the lectures, for one of the labs, and I did my best to correct it with the TA, so hopefully they'll send up a follow-up. But yes, we did have three lab, right? Monday would have normally been a lab, right? Would normally been a lab, but we had off yesterday. Okay? So, here's the thing. Friday is going to be lab 2 as normal for the people who were doing it on Friday. And Monday will also be lab 2, right? So then week 3 effectively starts on Tuesday for us. So think of it as basically that for this class, the week starts on Tuesday. So lab 3 will be on February 2nd for the Monday labs. Make sense? So you didn't miss a lab by having MLK, okay? I just want to be clear on that because I want to make sure that there wasn't any confusion with that email. So just simply do that. Now you can leave, but for the last 3 minutes I'm just going to pull up the assignment real quick and just talk about it real quick for those of you who do want to go over it a bit earlier, okay? Because if I have space, I might as well fill it, okay? Once again, if you have any questions on the assignment, feel free to reach out to me or the TA, okay? Lab 2 is made up of 4 exercises. Each exercise is worth 25 points. If, say, you only do 3 of 4, you'll get 75 points, and then when you turn in that last one, we'll grade it accordingly, okay? So, if it's late, turn in what you have is basically the point. Part 1 uses an old, I think it's from the equation, I think it's from the 60s, that calculates for a man or woman what the basal metabolic rate is. Again, it's an old equation, but I use this equation because it's easy. I don't need you to ask the user whether they're a man or woman. You just print out, if you're a man, this, woman, this. Make sense? We haven't learned if-else statements, so you just simply print it out. And then basically the idea here is that you're calculating the basal metabolic rate, which is the amount of calories you just passively consume to maintain your body weight, keep everything, all the machinery in your body running. It is the vast majority of the calories you burn, the typical person burns. Okay? Then I want you to take this and divide it by 214, which is the amount of calories that are in a typical chocolate bar, for a grand total of telling me if you did nothing but lay in bed and eat chocolate all day, how many chocolate bars would you need to eat to maintain your weight? I know, living the dream there, right? Please note that these are in American freedom units, not metric units. So now we go ahead and also look at number 2, debug my messy code. This code doesn't work. Figure out why. Next, this one's a classic one. In fact, I think it is in the textbook as an exercise. So it is ubiquitous. And finally, seconds to hours. This one is by far the most difficult one. Which I talked about already. Given 5,000 seconds, will give you 1 hour, 23 minutes, and 20 seconds, right? Fortunately, on Thursday, we'll be doing a number of exercises. One of them will be converting years to number of seconds, and seconds to number of years. That sounds kind of relevant here because to go up and down, we're going to need to convert all to hours along the way, So, in other words, this one's a freebie and this one's a freebie if you're paying attention. So, and for this one, just please put them in 4 separate files. That's a request, though. If you end up putting them in one file, just makes it a bit harder to test them all, individually. All right, with that, have a great day. Please be careful on your way home. Don't slip and fall. That hurts. Okay. And and feel free to come up and get any chocolate you want. Okay.